By the end of this episode, you will know how the virtual memory works, how paging helps your memory to be organized, and what happens when your system runs out of the RAM, and how it all affects the performance. Hello guys, welcome to the next episode of what every programmer should know about the memory. In the previous episodes, we talked about references, pointers, RAM, memory hierarchy. In today's video, we are diving deep into one of the fundamental concepts in the computer science called virtual memory. You might be thinking, I already know about the memory, it's RAM, right? Well, not exactly. The way that modern computers handling the memory is much more complex and intelligent than just using the RAM directly. So virtual memory is the reason that you can run multiple applications at the same time. Since the RAM is physically limited, if you want to run several applications at the same time by just directly access the physical RAM, the RAM cannot handle all the applications that you want to run. This could cause huge problems. Like for example, one program could overwrite what's already been written by another program into the RAM. It causes the other program to crash. So also if the RAM run out, it could cause the whole system to not run any new programs at all. And also each program needed to be manually configured to use different memory addresses. Virtual memory resolves this problem by creating something like an illusion. So it makes every program to think that they have access to the huge private free memory that they can assign all their data into it. Even the actual memory is much smaller. So how does this magic works? Virtual memory uses mapping system, and the addresses that program can see will be translated to the real memory. And these addresses, which is seen by programs, called virtual addresses. This translation is done independently for each program, and it allows every program to be isolated from each other when they want to access the memory. The key component which activates and enables this virtual memory is called paging. The operating system divides the memory into the small fixed size chunks, and these chunks called pages. These pages are usually small, like 4 kilobytes, but in modern system it can be 1 megabyte or even 1 gigabyte, depending which system you are using. So in that case, when the program uses the memory, it doesn't use the physical memory. Instead, it uses the virtual addresses that virtual memory provides. And these virtual addresses are mapped to the physical locations through the structure called page table. Imagine you are writing data to the memory address of 0x12345688. Your program thinks it's storing the data in that virtual memory address. But from the CPU, that's translated to another memory addresses like the one that it's shown below. The CPU constantly uses this translation to find out where the data is stored from the program. And by using this translation, it makes sure that every program has access only to the chunks that it allows to access. But where does this translation happen? This translation happens by the page table, a data structure that's basically maintained by operating system to find out where exactly the location of each virtual memory address is. The problem is that these page tables can get huge. For example, if each process needs millions of virtual address pages, just by keeping a mapping for every single one, this can take a lot of memory. That's why modern CPUs, they use optimizations like multi-level paging to organize this mapping more efficient. This means that instead of keeping one giant table for every single process, we can break it into the multiple layer, which means that we reduce the memory usage. This translation happens constantly, thousands or even millions of times per second. But there is a challenge. If every memory access requires to look up into the huge table to find the memory location, wouldn't that slow down the whole process of finding those data from the memory? That is where the translation look-aside buffer or TLB comes in. The translation look-aside buffer is a small high-speed cache inside the CPU that stores recently used paging that CPU tries to access. Think of it as a shortcut to the memory translation. If the CPU sees the particular memory address recently, it can bypass all the translation from the page table and retrieve it directly from TLB. Now we understand what is the paging. Let's talk about what happens when memory isn't available in RAM. Let's say a program tries to access virtual memory page that hasn't been loaded to the RAM yet. This triggers something called page fault, essentially a signal to operating system that it needs to retrieve the missing page. So what will happen in that case? The OS will pause the program, it finds the missing page on the disk, it loads the page into the RAM, it updates the page table, and then continue the execution of the program. For example, imagine that you open a really huge image into your Photoshop application. Your RAM is full, so some of the data will be stored on the disk instead of the RAM. When Photoshop needs that data, it triggers this page fault, causing the system to load that data from the disk into the RAM. And this you can feel it when you want to access some part of the image. It takes time for your application to load your image. But what happens if the RAM is full? So when this, for example, this page fault happens, the new page cannot be allocated to the RAM since RAM doesn't have any space. What will happen in that case? The system has a technique called swapping, where it moves some of these pages from the RAM into the disk. Usually it's called a swap file or swap partition. This frees up the RAM for urgent cases. By using this technique, you can overcome this problem. But if you use swapping, which allows your system to function even the RAM is full, it comes with a cost. Accessing data from the disk storage, where the swapping partition is located into it, is much slower than the RAM, as you know from the memory hierarchy video. As you may know, a typical RAM access can be 10 to 100 nanoseconds, while reading from SSD can take microseconds. That's 1,000 times slower. That's why when your computer runs out of the RAM, it slows down dramatically. You can feel it when you are using your application. It slows down, for example, your web browser, your Photoshop applications, or your games. Sometimes it takes too much even for your computer to respond, and you will see the high activity from your storage. If you have HDD or SSD, you can notice this non-stop working of your hard drive. So virtual memory is the essential part of the modern system. It allows us to use more memory than physically available. It avoids any conflict between different programs, and it isolates them to avoid this direct hardware conflict. It comes also with a cost. So always optimize your program to avoid any page faults. Monitor your program when it uses the swaps. The more swap that your program is using, it means that your program will be much slower than what it can be. And it can cause also the system which is running your program to slow down. And always use memory profiling tools in order to detect inefficiencies and monitor how your program access to the RAM. In the next episode, we will explore the CPU caches and how they interact with the memory. If you enjoyed this, don't forget to like, subscribe, and drop your questions to the comment below. Until the next video, good morning, good afternoon, and good night. Bye.